Hi everyone! So in this video, we're going to go ahead and learn about heating curves. So let's go ahead and get started. So quite simply, a heating curve describes what happens to a sample as heat is applied, and we can see how the temperature changes. So if we look at this graph off to the side, we can see that we have two different axes. So along the y-axis, we have the temperature, which is usually in degrees Celsius, but can also be in Kelvin. And along the x-axis, we have time. So as time progresses and we add more heat to the sample, what happens to the temperature? Well, initially, we're going to start with a solid in this case. Sometimes we start a little bit higher temperatures, but in this case, we're starting off as a solid. Then we have a horizontal line, which is a sign that we have a phase change, meaning that it's melting. Then we have another diagonal line, meaning that the temperature is changing as we heat up that liquid. That next horizontal line means that we are boiling our substance. And then the final diagonal line is the gas that, again, we are heating up our substance. So during a phase change, the temperature remains constant, even though we're putting more heat into the sample. That is because the energy we're putting into the system is going into overcoming the intermolecular forces and separating molecules. Now, one thing I want to point out here, for all covalent compounds, we are not breaking bonds. We're just overcoming intermolecular forces and separating the different substances. And then when we're not undergoing a phase change, we have those diagonal lines because the temperature is increasing. This is because the energy goes into increasing the average kinetic energy of the particles, so they start to move faster. So this also gives us two other definitions to know. One is the heat of fusion, which is shown as delta H subscript fusion. And this is the energy needed to melt 1 gram of a substance at its melting point. So in the case of water, it is 0 degrees Celsius. So the sample's already at 0 degrees Celsius. It's just in the solid form. And now we're going ahead and we're changing it into the liquid form. So how much energy does that take? The heat of vaporization is kind of the same idea, but it has to do with vaporizing or boiling a substance to get into the gaseous state. So if we're already at the boiling point, so for water 100 degrees Celsius, how much energy do we need to actually separate those molecules and get into the gaseous state? Okay, so one thing I want to point out is that usually the delta H of vaporization is larger than the delta H of fusion. That is because when we are vaporizing something, we're taking particles that are close by and we're spreading them super far apart. When we are melting something, we take things that are side by side and we add a little bit of space. Because there's more space or more distance increasing, that requires more energy. So again, we can see this if we look at the lines. That horizontal line for melting is pretty short, but the horizontal line for boiling is much, much longer. So it takes more energy. So there's some different constants. You do not need to have these memorized. Just know they are in your notes. You can use them whenever you need them. The delta H of fusion is 6.0 kilojoules per mole. And again, the delta H of vaporization, and these are all for water, by the way, is 40.6 kilojoules per mole. So quite a bit larger. Also, some specific heat values. Notice the specific heat changes based upon what phase you're in. So ice, water, and steam all have different specific heat values. Okay, so when it actually comes to solving problems involving phase changes, there's a few different steps to help you out. The first thing I recommend is that you write down your givens and your unknowns. So you're going to break your problem into different parts, and then you're going to consider what variables you're being given. Next, you need to figure out which equations to use. So anytime you have a change in temperature or one of those diagonal lines, you're going to use Q is equal to M times C times delta T. We've seen that before. It's shown back up. For phase changes, we have a simpler equation. It's just Q is equal to the number of moles times the delta H, which is either going to be the delta H of fusion or the delta H of vaporization, depending upon whether you're melting and freezing or boiling and condensing. Then you're going to solve for all the individual parts, then add the different parts of the problem up. Make sure you're watching for different units for kilojoules and joules because you can only add things that have the same unit. Okay, so let's go ahead and try out some examples. Okay, so let's go ahead and try out this example. How much energy in kilojoules, that's what we're trying to find, is required to heat 20.0 grams of ice from negative 7 degrees Celsius to 25 degrees Celsius. So the first thing I want to do is go ahead and break down our problem into different parts. And there's actually two different ways you can do it. One is you can actually draw out that heating curve like we know it to be. Or if you want to save time and not have to draw all that graph out, sometimes I just kind of use a number line. So when you're doing this, you want to think to yourself, what happens to water between -7 degrees Celsius and 25 degrees Celsius? Well, hopefully you're saying at 0 degrees Celsius, we are melting. Okay, so that is one key thing. So once we know those parts, we can start to break things down and then figure out what equations we need. So I've already actually broken this problem down into the 3 parts we're going to have. So we're going to heat the ice from -7 degrees Celsius up to 0 degrees Celsius. Once we get it up to its melting point, we're then going to go melting. And then once we've melted all of that ice and now just have water, we're going to heat it up again until we get to 25 degrees Celsius. So we're actually going to have a few different equations we're going to use. So whenever we have heating, we're going to use the Q is equal to M times C times delta T equation. Okay, so that is part 1 and part 3. Q is equal to M times C times delta T. Now, when I am undergoing a phase change like melting, I cannot use this equation because I don't have a delta T, but I know I'm still putting energy in. So for this one, I'm going to use Q is equal to the number of moles times the delta H. And we need to think, are we melting and freezing, or are we boiling and condensing? In this case, we are melting, so this is going to be the delta H of fusion. Okay, so from here, we can go ahead and actually start to plug in our different values. So you're going to need the constants in your notes, so go ahead and pull those up to help you out. Okay, so Q is equal to M times C times delta T. So we have the mass that is given to us is 20.0 grams. The C is the specific heat, but we do have to be careful here because we don't have liquid water, we have ice, which if you look at your notes has a different specific heat, which is 2.077 joules per gram degrees Celsius. And then we're going to have our delta T, which is our final minus initial. So 0 minus a -7. Okay, so if you're subtracting negative, that's like adding it. Okay, so we have a positive number there. So now we're going to multiply those values together. So Q is equal to 20 times 2.077 times 7. Go ahead and plug that in. That is 290.78. And if we think about our units, grams cancel out, degrees Celsius cancel out, leaving me with joules. Now, I'm not going to think about sig figs yet. I'm going to wait until the very end and then figure that out later. Okay, so the next thing, we want to find out how much energy is needed with melting the ice. Well, we need to know the number of moles, which we don't have yet. We have the grams. So we're going to need to do a quick conversion. So 20.0 grams of H2O. Okay, and we're going to need to know the molar mass of water. So 2 times the mass of hydrogen plus 1 times the mass of oxygen. So we go ahead and do that. That gives us 18.01, or right around there. So if we go ahead and plug that into our calculator, 20 divided by 18.01 is 1.11 moles of water. Okay, so now I'm going to go ahead and plug that value into our equation. So 1.11 moles of water. I'm going to multiply that by the delta H of fusion, which is 6.0 kilojoules per mole. Okay, so 1.11 times 6 gives us 6.66. In this case, the moles cancels out, so we are left with kilojoules. Okay, next one, we are heating 20 grams of water from 0 degrees Celsius to 25 degrees Celsius. So again, we're going to use that Q equals M times C times delta T. The mass is still at 20 grams, doesn't change. The C is now the specific heat of water. So that is the 4.184 joules per gram degrees Celsius. And then we're going to have our delta T, which is our final temperature, 25, minus our initial, which is 0. Okay, so now we're going to go ahead and multiply those three numbers together. 20 times 4.184 times 25. So that gives us a Q of 2092 or 2092. And again, we're going to have joules because grams and degrees Celsius cancel out. Okay, so now we have each of the individual parts and pieces. So the last thing we need to do is actually add these together. So one thing I do want to point out, we have one unit that is in kilojoules and then the other two that are in joules. We are asked to find the kilojoules. So I'm going to need to divide my joules by 1,000 in order to get the kilojoules. So 290.78 becomes 0.29078 kilojoules. And 2,092 becomes 2.092 kilojoules. Okay, so now we're going to add up these three numbers, each of them in kilojoules. And again, we'll think about sig figs when we are all done. Okay, so Q overall is equal to Q of part 1 plus part 2 plus part 3. So I'm going to take the 0.29078 plus 6.66, get my plus sign, plus 2.092. Okay, so if we add all of those together, 0.29078 plus 6.66 plus 2.092, we get out a value of 9.042, blah, 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 kilojoules. But now I want to think about sig figs. Okay, so if we go back to our original problem, we have 3 sig figs here, but only 2 sig figs for each of these numbers. So we're going to round our answer to 2 sig figs. So 9.04 gets rounded to 9.0 kilojoules. Okay, so I know that was a lot of different steps, but let's review it really quickly. The first thing we want to do is we want to go ahead and break our problem up to find the different parts of it. In this case, we knew we had to have melting in the middle. We're then going to figure out each of the steps. So we have heating of the ice, melting of the ice, and then heating of the water. We're going to use the different equations. Whenever we are heating our sample, we use a Q is equal to M times C times delta T. Anytime we have a phase change, we use Q is equal to moles times delta H. In this case, it's a delta H of fusion because we are melting. Otherwise, we pretty much plug and chug our numbers. Few things to watch out for. Remember to check on the different specific heat values. To find the moles, don't forget to convert using molar mass. Finally, get each of your units into kilojoules and then add them all up and round at the end. So now I have for you a problem to try on your own. So how much energy is released when 50.0 grams of steam is cooled from 109 degrees Celsius to 10 with a decimal point degrees Celsius? So go ahead, try this one on your own. Once you think you have the answer, come back and we'll go over it with the next video. Okay, bye everyone.